components and the whole construction of a DB2 relational database have been around since early AS400 days. That means they have been there inside the operating system, available for use for close on, I don't know, 20, 25 years. And it's my mission in life to make sure that one starts getting the benefits. Everybody starts getting the benefits of something that's been there for so long. It's crazy that we're not using it. So, these are tools to make your life easier. These are components that are going to make the database more intelligent and easier to use and easier to define and more agile and all of these lovely words. And of course, this cartoon again, don't fall into this trap of being so busy shoving your cart with square wheels across the ground and ignore the advantage you can get from doing this modernization job. I'm the guy on the left. Don't be the guys on the right, please. Thank you. DB2 components. The main component of DB2, the IBM DB2 database, is the physical database itself. That is a set of one or more data files defined to contain physical data. Obviously, it's best to have them normalized to third normal form, these physical database files, because they're going to give us the best balance between flexibility and ease of use. And actually, people forget that the physical database file is, in fact, a component of the database and must be seen as such. It's not part of the application. It doesn't belong to the application at all. Okay, I have a date, 1991. So that was when these functions from the DB2 relational database have been available to us. So the physical files themselves, normalized, are the number one component of a DB2 database. Then, the trick here, it's an IBM I DB2 relational database. I stress the word relational because this is what this database is. It is a set of physical files that are related together by definitions called constraints. These are part of the database. The constraints have absolutely nothing to do with the application. They have to do with the data contained in the physical database and how it relates to other data contained in other normalized tables within the database. There are four types of constraints. There are primary key constraints. A primary key, by definition, is unique. And every single physical file in the database must have a primary key, which is unique. Without that uniqueness, we cannot define relationships between physical files. Sorry, tables, for those who want to be purist. We need these unique keys in order to create relationships between files. File A is related to file B. You can't have records in file B if you don't have record in file A. But file A must have a unique key, because if you've got two records in file A, you can't create a relationship because you have a mess. So primary keys on every single physical database file. Then we have additional keys, which are additional unique keys. This is something that people are not aware of. I can build relationships between physical files using multiple unique keys. I don't only have to build relationships on one key. I can have 6 unique keys on a physical file. And I can use those unique keys for relationships to other files relating data in different ways. The other use for a unique key is to ensure that uniqueness is applied to fields that you would not otherwise include in a primary key. For example, a company name. You can make a company name a unique key, which means that you cannot have 2 customers with the same name, even if they happen to be 2 different customers. This is possible, I've seen it. You can't have ABC Shoes as 2 different customers because you make their customer name unique. You can use unique keys in that way as well. So the unique keys are a very powerful element in forming and constructing a relational database. Then we have a constraint called a check constraint. This is essentially a where clause, a SQL where clause without the where. It defines certain conditions around certain fields within a record, i.e., indicator can only be a Y or an N, or this value must be greater than 0. Now, check constraints are very useful. They're very quick and easy to apply to files, and they can be drink of water. They can be very powerful, very easy. You can have up to 3,000 characters per check constraint. So it can be a reasonably long where clause, which of course immediately begins to make it complicated. But you can have multiple check constraints as well. Same way as you can have multiple unique keys. So you can create quite a complex set of validations, because that's what check constraints are. They are validations on that particular file, but they are constrained to work within a single file. A check constraint cannot work beyond the boundaries of the file for which it is defined. As a result, you can't test that the value in this field is equal or is greater than the value in another file, in a field in another file. That you can't do. The fourth constraint is the big one. It's the referential constraint. The first 3 are all based on the file for which they are defined. But the referential constraint allows you to define a relationship between 2 physical files within a database. Now, we will go into each one of these in a lot more detail, and we will look at exactly how they work. But the referential constraints are the things that allow you to build your relational database, because they define the relationships, one-to-one, one-to-many relationships between physical files in the database. Now, there is a limit to the number of constraints that you can have on a single physical table. And I know that when I specified this last time, the last time I looked, it was 300. i.e. you can have 300 constraints on each physical file in the database. However, I think actually somebody looked it up and corrected me and said it was a lot more than that now. But quite honestly, 300 is an awful lot. So to have more is just an awful lot more. Okay, so the constraints made up of 4 different constraints form components of the database. Right. Then we have journals and receivers. Go into more detail a bit later, but journals and receivers are necessary for a fully defined DB2 relational database. So if you have not got into journals and receivers in your database, you need to start seriously thinking about it. We will talk about ways of implementing them, which are easy to manage and don't give you a great deal of hassle. But you cannot define referential constraints or check constraints without journals and receivers, because journals and receivers are used to manage the potential situation where you apply a record to the database and check its references, only to find that they're not valid and they have to reverse the update out again. So journals and receivers are used to manage referential and check constraint validation. And then commitment control. I insist, absolutely insist, categorically, absolutely insist that when you build a proper normalized database, you develop it in, around, and with commitment control. What we're trying to do here is we're trying to protect our database from all sorts of things, including accidental power failures that occur in the middle of a transaction. What you will find happening is as you start normalizing your database, you're going to get more and more files, and they're going to get smaller and smaller. Your applications will start processing transactions, and they will end up, a single transaction may update a dozen files in the database, with the knock-on effect that you will see from triggers. You could be updating a dozen files in the database. And if during that process you have a power failure or a system crash or a program error, you could end up with half-completed transactions in the database. And they are, if you face this at any time in the past, they are the absolute devil to clean up and get sorted out and make right. If you want to do it programmatically, you have to do or jump through hoops in order to make it right. Using commitment control takes all that problem and responsibility away. It protects the database from partial update as long as you utilize it correctly in your applications. But it needs to be an absolute non-negotiable part of the database. Those are the components that are actually, truly, and specifically part of the operating system to support DB2 relational database. There are 2 other things. Oh, sorry, I missed one. Why did I miss that one? I lied. There's the last one, which is absolutely and definitely a part of the physical database, and that is trigger programs. Or if one is going to be correct, triggered programs. These are programs written in any language you like, as long as it's RPG, in my case. you can hook them to any physical data file in the database. We will go into triggers in a great deal of depth because their power is beyond imagination. But they associate themselves, or you associate them, with a physical file. And those programs, through the database management system, create the intelligence that the database needs to become completely self-aware. And you write them in RPG, simple enough, easy to maintain, easy to test, and they attach themselves, or you attach them to a data table, a physical database file. And once they're attached, they are autonomous, and they do the job and protect the database without you having to worry about them. And they are definitely the thing that makes this whole thing work. So that list of components are operating system defined and operating system implemented. The trigger programs that you write in RPG that are attached to a physical database file run at priority 0 in the machine pool. If you are aware of any or understand work management on the IBM I, you have a machine pool, which is where all the operating system runs, at a priority 0, which means that it has preference over everything. And because the trigger program is part of the database management system, it runs there as well. So the performance from trigger programs is absolutely and utterly unbelievable. And you can do some experiments to prove it to yourself. Right. Having been caught once, I'm looking, and now I'm not going to get caught again. There is another element, which I call input-output servers. One of the things we want to achieve is we want to decouple, unlink, separate, tear apart, whatever you like to call it. We want to take the database away from the application, and we want to give it its own agility, its own management, its own intelligence, and we want to separate it from the actual processing that is done by the application. And the main tool to do this, the main tool that is used to do this is the input-output servers. Input-output servers are RPG programs, usually written as procedures and bound into a service program. And in my case, recommendation is one server for each physical file in your database. These are border control. They control the type of access that people have to database files. And in fact, I will show you techniques where, in fact, they protect your database from unauthorized access by a SQL client that somebody has downloaded from the internet. The input-output servers, together with the trigger programs, together can make your database completely impenetrable to anything except authorized programs, and it can be done without requiring any effort or management by anybody on your part. It becomes a natural consequence of how you put these together. And of course, details of those to follow. So input-output servers, although they may appear, they're not officially a part of the database components per se. I see them as part of the database components. In fact, every time I create a database file, I define its constraints, set up its journaling commitment control, I define and code trigger programs for it, and I code and compile an input-output server for it.